Okay guys, we're coming to the end of a long and certainly challenging 8 weeks. It seems a lot longer than that, but we're certainly coasting into a finish here. If you've been paying attention to the videos and paying attention to the emails, you know that test number 2 is already posted. Test number 2 will be up until Friday at midnight. After that I need to close it so that I can collect the grades and start adding up numbers in anticipation of the final, which will be Monday the 12th at 5:30 to 7:30. It has to be a time test, unfortunately, because it's basically a take-home test. So that was a provision that was put in since your class isn't the only one taking this test. So anyway, I'll be reminding you periodically to watch for that time slot. Make sure you get in there and take the test. It will be extremely difficult to fix any problem with regards to that. Obviously the school administration isn't at the building. Just trying to track somebody down and trying to figure out how to deal with a missed test at this point would be very difficult. My grades have to be in by noon the next day. So I need to have you finish up by 7:30. The system will give me your scores, of course, and I will calculate the scores. What I'll do is I have numbered grades for all 3 tests. I'll calculate a letter grade, but unless you selected that, which I think only one person has, you will get a pass-fail. So there's an ABC pass-fail and a D pass-fail or something like that. There's some pass-fail level that if you're at that sort of D level, it isn't quite the same thing. I have no idea what standing those have in your academic record. I don't think anything. So I don't think there's any consequence to not taking a letter grade. But what I will do is, if you ask specifically, if you send me an email, if you send me a text, I will tell you what your letter grade would have been, just if you're curious. If you send me a text, you absolutely positively have to tell me who you are, because I can't tell from your text phone number. Okay, so that's all preamble. I still have some material I want to cover, a little bit on position yet, but I'm not going to spend much more time on that because it gets progressively more complex, but I do want you to be exposed to composite controls a little bit more. There will be a question, I think, on the final with regard to that, and then we can very briefly go through runout. So in another video or two I should be able to have all of that stuff out. My intention here today is to present a review. It'll be this video and maybe another one depending on how the time goes. I'm going to emphasize the 2 aspects of the final. One aspect is my experience with the final, which is people make the most mistakes with the simplest concepts because it's carelessness or it's forgotten from 8 weeks ago. So I'm going to kind of dredge up some of the older stuff about conventional dimensioning and tolerancing and limits and unilateral and bilateral tolerancing and all of those things that are really fundamental to dimensioning and tolerancing at all, and certainly for GD&T. So we'll review that a little bit. If you follow along and take some good notes, you'll have a good study guide. With that in mind, I have also posted a study guide or a cheat sheet. It's on Canvas. No, actually, I emailed it to you, so you should all have that. So in conjunction with the videos, and in conjunction with your notes, and in conjunction with the cheat sheet, the final should not be any challenge at all. If you don't make the most common mistake, which is being careless with your numbers. Okay, I've told you on the cheat sheet, and I'll tell you forevermore that you have to make sure you know what the number is. 10 thousandths isn't 1 thousandth. It looks very similar, but it's not. So in the course of manipulating dimensions and tolerances, you've got to do the arithmetic right, and the consequences on the final are pretty great because you won't get a chance to recover from it if you miss these. The final is weighted a little heavily towards some of that earlier material, which I think is a good thing because it's the most fundamental. All the true GD&T, all the symbols, all the feature control frame stuff, that's in the standard. And when time comes, and it will come for you if you stay in the technical trades, you'll be asked to interpret some sort of GD&T. And unless you've really stuck with it for a while, it'll be a little hazy. So you'll have to go back to the standard and try to make sense of it. In terms of manipulating dimensions and tolerances, adding decimals, that sort of thing, the standard isn't going to help you. You either do it right or you don't. And the problem with any sort of number problem is it's either right or it's wrong. There's not much running room. And there are no essays on this one, so it's even hard to give you a partial credit. I think it'll be impossible on the final to do a partial credit. When they moved the exam to online, they made it basically all multiple choice. So that's good and it's bad in that regard. Okay, so on to the review. The first thing, and one of the most common mistakes I see on the final, is forgetting that in the old way of doing dimensions and tolerances, the bilateral, unilateral way of doing things, it's important that you remember that the dimension and the tolerance are really two different things. Now they're mixed up a little bit and sometimes you can't really tell one from the other in limit form, but from the point of view of tolerancing and GD&T, we want to make a clear distinction between the dimension portion of it and the tolerance portion of it. The dimension, which is this portion, is intended to be perfect geometry. It's supposed to be what the designer designed to. And if you made it right at the dimension and we didn't have to deal with tolerances, we'd all be happier, believe me, especially QA people. But this is sort of a fixed point or an ideal goal to have a perfect geometry. And that's what GD&T does, is it establishes sort of a perfect geometry around which we draw tolerance zones. And those tolerance zones can take a million different forms as you've learned already. But always make that clear distinction between a dimension and the tolerance. And that tolerance can take any number of forms: a bilateral, a unequal bilateral, equal bilateral, unequal bilateral, and unilateral. And you've learned, I hope, that we can convert from one to the other. And if we keep track of the limits and check against the limits in any form, we'll always have done it correctly. It's very easy to get mixed up in the numbers. So anyway, remember, dimension is the dimension, the tolerance is the tolerance. The tolerance can be expressed a number of different ways. Okay, so you should be able to, on the test, be able to pick out a dimension from the drawing and separate it from the tolerance. With that notion of limits and dimensions and tolerances, we have this concept called material condition. It's expressed symbolically with these two symbols in GD&T now, and I told you that at one time there used to be another symbol like that, but that's been obsolete for a while. That material condition relates to how much material there is in the feature. Okay, so is it a hole or is it a shaft? We have to make that first distinction about what is the gender of the feature. If it's a shaft, with a dimension and tolerance, or a hole with a dimension and tolerance. Whenever you come to this scenario, the very best thing you can do, no matter what form it's in, unilateral, bilateral, unequal bilateral, doesn't matter, convert that form into limit form. It's relatively easy. You add the dimension and the plus tolerance, and then the dimension minus the tolerance, and we end up with a limit form of 1 inch 5 thousandths and 995. And it's exactly the same limits here. And the dimension on the drawing could have been expressed in limit form. If it is, great, it's a good start. Okay, then you determine, after determining the limits, you determine the gender. This of course is a male and this is a female feature. And then we can determine which one of those limits is the maximum material condition for the shaft. The shaft that has the maximum material in it when it is at its largest or upper limit. And vice versa, when it's at its smallest, it's at its least material condition. Just the inverse here with the female feature. When the hole is at its smallest, the part has the most material. So this becomes the maximum material condition on the lower limit, and this becomes the least material condition. Take the time to write this stuff out. Don't try to sort it out in your head. You will trip yourself up, especially in a test. So keep that sequence straight. Whatever you start out with, dimension and tolerancing, express it as limits. Determine the gender of the part or the feature, and determine which limit is which. And you should be able to do that. That is a common error on the tests. I would say it's very easy to get confused. I just want you to be able to do all of these conversions from unilateral to bilateral to limit, back and forth, and if you can do that without a math error or arithmetic error, you're doing good. Okay, there will be conversion problems on the test. You'll have to convert from one form to the other. It's an important step in evaluating a tolerance zone, so make sure you can do that. When you do that, make sure you read the questions very carefully. The way the question is worded sometimes will trip you up if you ignore the way it's written. So make sure you read the question carefully and write the numbers out. Don't just read the question and go to the checkbox and check the one that looks right. Write them out and compare what you've written out to the answers. I do want to spend just a minute here in this review talking about, let me draw this a little differently, something that we briefly mentioned, but I don't think I focused enough on it, is the concept of stack up. Okay, so what we have here is a little step block. Each step is individually dimensioned. Each step is 1 inch, 1 inch, 1 inch. The tolerance here, let me write these out a little bit bigger. I'm not sure how small you can actually see. So that one is 1 inch plus or minus 5. This one is 1 inch plus or minus 3. And this is 1 inch plus or minus 1. Okay, now stack up is the consequences of tolerances. It is the effect of tolerances on overall sizes. This is a tremendous problem for engineers. It causes a lot of stuff not to fit or work properly. And engineers spend a lot of time dealing with stack-ups. It's a big effort on fairly complex things. And the reason is because the way things are dimensioned here with this plus or minus approach, or it could be plus nothing, minus something, it doesn't matter what form it is in, it is the same result, is that there's a number of different ways to dimension this, and the way you dimension it affects the overall dimension of this part. So if I ask you, what is the dimension of this part? Not the dimension of the tolerance, but what is the dimension? Well, you can add up the dimensions. It's 1 plus 1 plus 1. So the dimension is 3 inches. That's easily enough done, just adding and subtracting dimensions. Here, it's very easy because they're all the same. Let's look now at the effects of the tolerance and how those relate to the overall length of the part. Okay, so just like we added up dimensions, we add tolerances in the same way. Tolerances are additive just like dimensions. So I have a plus or minus 5, I have a plus or minus 3, and a plus or minus 1. So plus or minus 5, plus or minus 8, plus or minus 9. Okay, so if I look now at the limits of this stack up, I'll end up with 3.009 and 2.991, yes. So you see that the dimensions are cumulative, but the tolerances are also cumulative. Now, I did this across the entire thing, but you could say, well, what is the dimension from this point to this point? And you do the same thing. You add two dimensions for a total of 2 inches, and plus or minus 5 and plus or minus 3. So you get plus or minus 8. So it's not rocket science, but it does mean that all these tolerances are accumulating depending on how you had dimensioned it. Now, if I had not dimensioned it this way, but I did it in 2 steps. Would anything have changed? I could have done this one as plus or minus 5. And now the stack up across from here to here is just 5 thousandths instead of 8 thousandths. And the stack up across the entire part now is 2 inches plus 1 inch is 3 inches. And the total accumulation of tolerance is plus or minus 6. Okay, so we went from plus or minus 9 to plus or minus 6. That's a 30% reduction in the effects of the tolerance, just in how we dimensioned it. Both of these are valid ways of doing the dimensioning, but it does have an impact on the part. So this is something that is easy to overlook or to forget about, but how you dimension when you use these conventional dimensions and tolerances has a big impact on how things add up across the length of a part. Okay, now don't get flustered if, say, one of these dimensions or one of these tolerances is plus nothing minus 0.003. They add in exactly the same way. We still end up with 3 inches on the dimension And we have plus 5, plus 0, plus 1 is plus 6. And minus is minus 5, minus 8, minus 9. So if it starts out with one of those elements as a unilateral or an unequal bilateral, the result will be unilateral or unequal bilateral. Again, it really is just an arithmetic game, but it's a game that has significant consequences. And really, one of the reasons we go through GD&T and set up a system like that is to minimize those effects. GD&T does a very good job of minimizing the effects of stack up of tolerances. Okay, I want you to make sure that you remember too that when we have a dimension and a tolerance and we turn that into limits, we have this concept of the allowance, which is the total span of the tolerance. Some people get confused with the minus sign. They try to treat it as something other than just a change in direction rather than a change in magnitude. This isn't really a negative number. It just means that it's a shorter overall dimension, and this is the plus side is a longer dimension. So what that means is that plus or minus 5 is a total span of 10 thousandths, and that is the allowance. The allowance does not include the dimension. The allowance is just the span or the sum of the tolerancing. I'd say the sum, but it's really not the sum. It's not plus 5 minus 5. It is plus 5 and plus or minus 5. So a total of 10. So the allowance is not 1 inch 10 thousandths. It is just 10 thousandths. And always keep that as a separate number. We use that later when we start using the effects of material condition modifiers in GD&T. Okay, here is a very big problem. I want to nip it right in the bud. When we talked about the problems with dimensioning and tolerancing, and we said that we had dimensions locating the center line of this hole, and they have a tolerance plus or minus 5, plus or minus 5, that the dimension locates a perfect 1 inch by 1 inch location from the edges of that part. The tolerance defines a zone. And if we look at that zone with plus or minus 5 tolerances, you really zoom up real tight, so I'm zooming up right here and looking at this with a magnifying glass. We have a tolerance zone that is plus 5, minus 5, plus 5, minus 5, and that's that square tolerance zone that we said we really didn't like, and GD&T will solve, and it does. But remember that this is the size of the allowance. The tolerance zone is the size of the allowance in this direction, the size of the allowance in this direction. Okay, now what happens if these tolerances go a little haywire? Instead of being bilateral, let's see what happens if we make this one plus 5, minus nothing, and this one plus nothing, minus 5. Okay, so what does that do? Well, that shifts the tolerance zone. Where before with the bilateral tolerances, the tolerance zone was sort of centered around the dimension, the perfect location. Now, we're going to have to look at it, so the vertical tolerance zone is plus nothing, so it doesn't go anywhere up north, it stays right here. And it's minus 5. And it is plus 5 in this direction. And it is minus nothing. So that's where that tolerance zone is. The perfect position is still right here. So the tolerance zone is shifted way over to the left on this, in this illustration with unilateral tolerances. Depending on how these tolerances run, that orange box can move this way, it can move that way. It'll always contain the perfect position, but the perfect position could be right out on the edge of the tolerance zone. So as much as having a tolerance zone like this with square corners was a problem, it's really a problem when you're starting out with one of the tolerances right out on the edge. This thing is right out here in, on the border of that tolerance zone. So again, picture the tolerance zone, the orange box, shifting around depending on how these tolerances are expressed. Please remember, first mistake and most common mistake is this tolerance zone has nothing to do with this feature. It has nothing to do with the hole itself. We are talking about the center line of this. So even though that's a round hole, that doesn't mean this tolerance zone is round. GD&T will allow us to make it round if we want, but it isn't. It isn't round here. It's a square. If this hole were a triangle, this tolerance zone would be exactly the same. So the shape of the tolerance zone and the size of the tolerance zone are defined by these locating dimensions. Okay, I'm going to terminate this video at this point. There'll be another one here very shortly where we can continue on with this review. I'm going to run out of time on this tape.